The set of videos for today and the set of videos for next time are about two robotics concepts that are highly related. Today's videos are about a robotics problem that's called path planning. And the next set of videos are about a related problem called collision avoidance. I'm showing you a video right now of some people playing a game called Operation. And the reason why I'm showing this video is because this is one example of sort of the human version of the path planning and collision avoidance problem. If you've ever played this Operation game, you know that the goal of the game is to be able to use these little tweezers to remove objects from this game board without allowing the tweezers to touch the metallic edge of the holes. In this game, the object of the game relies not upon your ability to correctly position the end effector, the tweezers in this case, but it relies upon the player's ability to guide the tweezers through a specific path between its starting location and the location where you need to pick up these little objects. So today's videos are all about path planning. In our previous activities with the articulated manipulators that we built in class, we did not pay any attention to the path planning problem. We simply specified a starting and ending location for the end effector, and we allowed the manipulator to move between those 2 points in the default manner, which is maximum velocity for all of the servos simultaneously. Path planning in robotics is important for a lot of different reasons. One of the reasons is exemplified in the video that I'm showing here. It's a robotic painting video. Painting, if you remember way back in the beginning of Robotics 1, I noted that painting is one of the biggest jobs that robotics is employed to do. In the painting task, if you can see in this video, the path that the end effector takes is extremely important in the quality of the paint job that results. The end effector doesn't just move from the front of the car to the back of the car. It has to follow all of the different contours and evenly apply the paint according to the specifications for this painting job. The path planning problem is difficult for the same reason that the positioning problem that we learned about in Robotics 1 was difficult. And that is that we have to answer this particular question. The question is, how can we figure out what angles to move the servos through in order to move the end effector through the specified path? Note that if our manipulator is a Cartesian manipulator, that is, all three of the joints are prismatic, this problem is much easier. All we have to do is set the X, Y, and Z positions of the joints to match the X, Y, Z positions that we want the end effector to be in. But if our manipulator is not a Cartesian manipulator, if it has some or all of its joints revolute joints, in that case we have to solve this problem where we figure out what angles correspond to the X, Y, Z positions that we want the end effector to be in, not just at the beginning point, not just at the ending point, but at all of the points in between. The simplest way to solve this problem is to use a device that's called a teach pendant. This video is showing a couple of engineers using a teach pendant for their robot. You'll see that this teach pendant has 6 buttons with a plus and a minus, and the user can use these 6 buttons to change the angle of the 6 degrees of freedom of their robot. When the engineer gets the robot into a position that they like, they hit a button to record the joint locations at that position. You can then continue driving the 6 axes around to the next position that you want for your painting operation or whatever, and then hit the button again and continue on like this. It's a slow and painstaking kind of a process, but it's a way that you can solve the path planning problem without doing any kinds of calculations or whatever. This is a very user-friendly approach, but it's also slow and not very precise. And in this set of videos, I'm going to be showing you how you can do this path planning problem and be a little bit more precise with it and get a better solution out than you would if you were using this kind of a teach pendant, just slowly driving it around until you get it into a position you like and recording the positions. So the teach pendant approach has the benefit that it doesn't require the user to do any kind of calculations. However, it's not a very precise or optimal method for planning a path, and it's also very slow and tedious. In the next video, I'm going to introduce a new concept to you that's known as configuration space. We can use configuration space to do a much more precise and optimal method of figuring out the path that our robot end effector can take from point A to point B.